All right, I'm going to discuss two problems and homework 4 with you because they are a little bit difficult based on the questions I usually get from the students. So the first one is the question 12, problem 23.39. So let's take a look at this question. A long coaxial cable consists of an inner solid cylinder with radius A and an outer coaxial cylinder with inner radius B and outer radius C. So the outer radius is mounted on insulating supports and has no net charge. The inner cylinder with radius A has a uniform positive charge per unit length lambda E. Okay, so this is what we have. We have a coaxial cable which has an inner solid cylinder like this. Okay, so this is like a solid cylinder. And then there's another outer cylinder which is like this guy, okay, which is actually hollow but it has a thickness, okay. So that's why it says it still has an inner radius B and outer radius C, but anything smaller than B, nothing, okay. So then you're going to put this guy, this small cylinder inside this big one, so that's going to give you this coaxial cable, so that's what it means, right? So I've also drawn it here, so I hope that helps you visualize this coaxial cable. This is the small solid cylinder, right, inside. So this guy has a radius A, the problem says. The outer cylinder is it's actually a shell. It has an inner radius B and then outer radius C, but nothing between A and B, right? Nothing between A and B. There's a gap between A and B, okay? So the shell is solid, the small cylinders are solid, but nothing between A and B. The problem says that we're gonna now charge the small cylinder A. So I'm gonna charge this guy. So this guy has been charged uniformly and has a linear charge density lambda E. Okay? So let's see. We want to find the electric field at different points. Okay? So let's take a look at part C. Part C is pretty much like the rod we did in class. Okay? Because part C says find the magnitude of the electric field at any point between the cylinders at a distance r from the axis, which is you pick a point between A and B, right? You pick a point between A and B, so say this point, I pick a point at this point, right? So, and then what is the direction of the electric field? So this direction of the electric field, okay, let me just, the electric field only comes from this solid sphere, a solid cylinder, right? There's no electric charge here. So the electric field at any point actually is only produced by this guy, right? So if I redraw it here, so let's redraw this cylinder here. I want to find the electric field, say, at this point. How do I find that electric field? Again, use the symmetry, right? I can pick this charge, say, draw the electric field created by this charge in that direction. What about this guy? Totally symmetric. So the x components cancel, y components add, right? So what is the electric field at this point? If I want you to draw the electric field at that point for me, you would draw an arrow straight up, right? You would tell me that's gonna be the electric field at this point, right? Straight up. Now, what about if we pick this point? We can still repeat the same process, right? So you're gonna find like there are gonna be like two electric. If you pick this guy and this guy, you're gonna get electric field this way, electric field this way. So y components cancel, only x components have. And you can do the same thing for every little charge, so you will get the electric field in that direction. So the electric field created by this cylinder at any point outside this small cylinder, it's going to be always radiated outward because of the symmetry, right? And that's also easy to see, right? This point is totally equivalent to that point. There's no difference between these 2 points. If at this point you rotate this point 90 degrees, this point becomes that point. So that's why the electric field is going to go from this direction to that direction. But anyway, the direction of the electric field at any point produced by this this cylinder, it's going to be outward, right? So the direction is outward, okay, from the symmetry. So any point, I pick a point here, I want you to draw the electric field. I don't need to repeat the same process again. I know it's going to be radiated outward. So at any point, it's going to be this, right? At any point, which has the same distance from the center of this cylinder, the electric field is going to be outward, okay? So the electric field is always going to be outward at any point I pick between A and B, right? In this gap. This is going to be straight up, so this guy is going to be to that direction, down, and this point left, at this point it's going to be outward. Every point is going to be outward. Now I'm going to use Gauss's law. So that's the direction. Direction, you don't need to do any math, right? We have a lot of experience. We have done a lot of problems. You just use the symmetry. You can always figure out the direction, okay? Now the magnitude, you're gonna use Gauss's law. And if you use Gauss's law, the flux equals this, E dot dA, and this must be equal to Q inside over epsilon naught, right? And then if you do this, this is pretty much like the rod we did in the lecture. So you can review that, because what you're going to draw is going to be, you draw a cylinder, okay? You want to put all these points on the same surface. So when you integrate that, the electric field, the magnitude of the electric field is going to be a constant, right? What's the difference between this point and this point? There's no difference. They are equivalent. So the magnitude, of course, the direction is going to be a little bit different, but I can still say at every point, the electric field is radiated outward. But if you draw it out, the direction is different. The magnitude must be the same, right? Because there's no difference between this point and this point. So if you want to put all these guys in the same surface, you're going to draw a cylinder like what we did with the rod. So I can review the lecture on the rod. And then you don't just use this surface, okay? You're going to draw a whole cylinder, which is a little bit bigger than. So this is a cylinder you draw, so, right? So that's what we did in the rod problem, right? If this is a rod, right? So you can consider the cylinder inside as also a rod, right? It just have some size. You're going to imagine you draw a cylinder, okay? So the rod just goes through the center of that big cylinder, totally imaginary, okay? Doesn't exist. You use that to help you find out the electric field, right? So that cylinder is actually between this guy and this big hollow cylinder. So you draw something between them, right? You draw something, imaginary cylinder between them to help you find out the electric field at any point between A and B. So this is a cylinder I draw. That's my Gaussian surface, right? And then the steps are going to be the same as the rod. Now you see that you're pretty much just calculating the electric field created by a rod, right, at the center. So you would just do, because this is a cylinder, is a Gaussian surface, the whole surface of the cylinder is a Gaussian surface, because Gaussian surface must be closed always. Then you would do this, right? The top surface, E dot dA, the bottom, and then the curved side. It's going to be Q in over epsilon naught, okay? And then the top and the bottom, like what we did with the rod, because the electric field radiate outward, so they're all parallel to the top and the bottom of this imaginary cylinder you draw, right? Because this is the imaginary top, electric field all going in that direction, parallel. Parallel and parallel, you always get a zero, right? So don't be afraid of the integral. In Gauss's law, we never evaluated any integral in this part, okay? So this is going to be zero, this is going to be zero. It's always going to be the special cases we saw. It's always going to be these special cases. So the left-hand side is actually easier than the right-hand side. Okay, don't be scared by the integral. The left-hand side is easier than the right-hand side. The right-hand side can be tricky. The left-hand side is always going to be the special cases. Now the curved side, we did that with the rod, right? The curved side, because the electric field is perpendicular to the surface everywhere. So it must be E times A. It's always going to be E times A. And that E is what I want to find, right? The electric field at a point which has a distance R. Now I'm going to call this distance R because it's going to be the radius of this imaginary Gaussian surface I draw, so we call it R. But if you don't like small r, you can use any symbol you like, right? A lot of people, they will say the small r and the big R, they're confusing to me. In this case, we don't have any big R. They're not confusing at all. It's not confusing at all, right? If you don't like bigger, little r and big R together, you can call this guy D, X, Y, Z, whatever symbol you like, okay? Now this is E times A, Q in over epsilon naught. So how do I find the electric field? Don't forget what we're doing. We're still trying to find the electric field. So it's going to be Q in over epsilon naught A. Right? So now the A, what is this A? We only integrate this E on the curved side. So the curved side is going to be the area of a curved side of a cylinder. It's just you open it up, it just becomes a rectangle, right? So you're going to do length times the width, which is just going to be the circumference of the base times the height of the cylinder, right? So in this case, the A is just going to be 2 pi r times h. But the problem doesn't give me the h, right? So that means at the end, you should be able to cancel this h, this totally arbitrary variable introduced. You should be confident, okay? If you do things in the right way, the symbols you introduced should be canceled at the end. How does it cancel? Well, this Q in, right? How do you find the Q in? Well, if this is the Q in, it's always the charge inside the Gaussian surface you draw. This is the Gaussian surface I draw. It's bigger than this real cylinder which carry charge, right? So how do I find the charge inside this imaginary Gaussian surface I draw? Well, this whole cylinder, real cylinder with radius A, is totally inside the imaginary Gaussian surface I draw. So all I need to do is just calculate the charge on this this real cylinder with radius A, right? How do I calculate that charge? Well, the problem says it has a linear charge density. It has a positive charge per unit length, lambda E. So now you can treat it as a rod, right? It's just telling you, you think of it as a rod. It has a linear charge density, lambda E. What is the total charge on this cylinder, on this rod? Take a look at it, right? For each unit length, it has a charge lambda E. How do you find the total charge of this rod? Well, I'm just going to do lambda E times the length of this rod, which is just the height of the cylinder, right? So in this case, Q in, it's going to be lambda E times H, right? I can just think of this cylinder as a rod, okay? Now you put them together, you see this H is going to cancel. So that's going to be part C, okay? The magnitude of electric field at any point between the cylinders, so that's between A and B. And then part A is a little bit tricky. Now you're going to find the electric field inside this inner cylinder. So let's draw it again. So I'm just going to only draw this cylinder with the radius A. Okay, so this guy has a positive charge. Now I'm interested in a point, say, let's draw a point, pick a random point. This point. Again, I'm going to call the distance R. I use this symbol R, so I'm going to use this symbol in my final expression. I want to find the electric field at this point, or this point, right? As long as it has a distance R from the center. Again, what is the direction of the electric field at this point? We've done this so many times. The electric field must be outward, right? radially outward, because this is all positive, it's totally symmetric. Outward. What is the electric field at this point? Also has a distance r from the center. Outward. 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 Right? So again, I'm going to draw a Gaussian surface, totally imaginary, doesn't exist. It's not a real surface. It's totally mathematical tool. Okay? So I'm going to still draw a cylinder, right? If I want to put all these points in the same surface, and then I want to get a closed surface, right? So this is going to be the small cylinder. So it's even smaller than the cylinder with radius A. So this is a cylinder with radius A, but I'm drawing a cylinder with a radius R, which is even smaller than A. This is A. So I'm going to, again, apply Gauss's law in this small cylinder I drew, totally imaginary, doesn't exist. Totally imaginary, doesn't exist. Okay? So this is the cylinder I drew. The same step, because the cylinder, if you want to integrate the cylinder on the surface, you're going to break it into top, bottom side. Top, bottom, the same, because the electric field is radially outward. So parallel to the top, parallel to the bottom, 0, 0, nothing has changed, nothing. So you still get E times A on the curved side, because perpendicular to the curved side, perpendicular to the curved side, perpendicular, perpendicular, nothing has changed. How do you find E? Don't forget what we're doing. We want to find E. Rearrange this equation. You get Q in divided by A times this curved side, right? Excuse me. The A of the curved side, what is the area? You can still do 2 pi r times the height of the cylinder. So this hasn't changed. Nothing has changed so far. What is the Q in? The Q in, remember, this is not the Q in I should plug in, because this Q in is what I just calculated on this whole cylinder with radius A. But in this part, if I'm interested in a point inside this cylinder, okay, I only need this portion of this charge. I can't just use lambda E times H, which is going to be this, because this portion, right, this portion is not inside my Gaussian surface. I shouldn't include that in Gauss's law, otherwise I'm making a mistake. I'm not getting the right answer. So I should get rid of that, okay? So how do I find out the electric charge only inside this very small imaginary cylinder I draw? Take a look at the difference between this small cylinder and the big cylinder, right? They both carry charge, right? I'm just picking this small cylinder out of this big cylinder, okay? So the charge, if I can find the ratio between them, right? If I can find the ratio between this charge on this small cylinder with the radius r and the charge on this big real cylinder with the radius a, so that I can rearrange this equation and multiply. If I find the ratio is like a big X, and then I just multiply them together to get this QR. Why? Because this QA, I found it, right? This is just going to be the charge on this real cylinder with this radius A. That's what we just found in part C, right? That's the total charge on this cylinder. So if I can find the ratio between them, I just multiply the ratio, whatever I will find, with this lambda E times H. So that's going to be the charge inside this small cylinder. What is the ratio between them? What is the difference between them? Difference between them is this guy is smaller than the big guy, right? And this guy is going to have a small volume than the big guy. So the charge on the small cylinder and the charge on the big cylinder, the ratio between them is just going to be the ratio between these two volumes, right? Because they both carry charge. I'm just picking out this small volume out of this big volume. So what is the ratio between the charge? That's just going to be the ratio between these two volumes, right? Because that's the only difference between these two guys. What is this volume of this small cylinder? That's going to be the base times the height, pi r squared times h, right? What is the volume of the big sphere, the real sphere with the radius a? Pi a squared times the h, right? Now if you cancel them, what do you get? You will get this ratio equals r squared over a squared. All right, so if you have the ratio QR over QA equals r squared over a squared, you can find the QR equals r squared over a squared times this QA. This is the QA found, lambda e times h, right? So, and that's just going to be the Q in I plug in and this part, right? So this is going to be the Q in you plug in, and that curved side still have this, has this area. And then you put them in, you will get the expression for the electric field at any point inside this real small surface with radius a, right? So that's the expression for that. Your expression is going to still have r, lambda e, and then you're still going to have a, because you have a there, right? And epsilon naught. So that's part A. Now part E, find the electric field at any point outside the outer cylinder. So that means I pick a point even outside everything. I would pick a point here, right, or here, if they have the same radius. But if you want to find the electric field at this point and this point, the electric field is still created by this guy. Right, you still repeat every process. You're going to still draw an even bigger cylinder. You're going to draw a really, really big cylinder, right, as the Gaussian surface, totally imaginary, it doesn't exist. You're going to repeat the same process. Everything is going to be the same as part C, right? It's going to be the same as any point we calculate here. Because the charge inside is still going to be the charge on this cylinder, right? And the area is still going to be 2 pi r times h. So everything is going to be the same as part C, as this point, okay? So you will get the same expression. This expression is going to be the same. Because this shell doesn't carry any charge, so it's not going to make any difference in this question. It's not going to make any difference in this question. Okay, because the Q in is the same. If you pick a point here or here, the Q in is the same, so it's not going to make any difference, right? Now, so we have finished this. Let's take a look at the next question I wanted to discuss with you. Question 13, the last one, 22.57. So part A is this. A sphere with radius r has a uniform positive charge density rho e. We want to find the electric field inside the sphere at a point r from the center. Okay? So, and we have done that in class. So you're just going to redo it. The only difference is that now the question already tells you the rho e. Okay? Already tells you the rho e. So you don't need to find rho e by doing the big Q, the total charge, divided by the volume of this sphere. Right? You just go ahead and use rho e. Okay? So that's the only difference between this question and the question we did in class, because we did the sphere in class. Okay? Review that. So you will get a function. Okay? So as rho e epsilon naught and then the r, because the r is going to be the distance from the center and to the point you want to calculate. So the r is a variable, and these two guys, they're constant given from the problem. And what is the direction of the electric field at any point? Well, that's going to be outward. Right? We also did that in class. Okay, for a positive sphere. It doesn't matter if it's inside or outside. The electric field is always outward. Now part C and part D, well, we just replace that with a negative sphere. And then we want to find the magnitude of electric field, right? The same, okay? So the expression is going to be the same, right? You replace the positive charge with negative charge. The volume charge density is still rho e. You do the all the math exactly the same, right? The only difference is the direction is going to be reversed, right? If it's an active sphere, what is the direction of the electric field at any point, inside and outside? That's going to be inward, right? Now part E, okay, so you will actually get the same expression, okay? So these two expressions are going to be the same. There will be no difference. It's also a function of rho E, epsilon naught, R. Okay, these two expressions are the same. Now let's take a look at part E. Part E is a little bit tricky. So now I don't want you to calculate anything on this positive sphere or negative, because I already know that. Right? Now I'm going to give you this. A sphere with the hole, so which is very different from what we did, okay? So I'm going to still charge this sphere, but because there's a hole here, so there's no charge inside this hole, right? So that's the problem, what this question is. So there's no charge inside this hole. And then the problem wants you to find the electric field at a different points on this guy. So this is a little bit crazy. We never learned how to find the electric field from a sphere with a hole in it. And this is not symmetric at all, right? You see, there's a hole here, but there's no hole there. There's no hole there. So this is not symmetric. If you want to do this guy using Gauss's law, that's really hard, okay? Because you don't have a good symmetry to use. What we're going to do is this, okay? Think of this as equivalent to a solid sphere. No hole at all. Positive charge. And then make a small sphere which has negative charge. And put this small sphere right at this point where this hole is supposed to be. You put this negative sphere right at this point, so the negative charge is just going to cancel all the positive charge here. So if you combine these two guys, you will get this guy, right, equivalently. So I don't know how to find the electric field created by this crazy sphere with the hole. But I know how to calculate the electric field created by this guy, because this is a perfect positive sphere. This is a perfect negative sphere. I can find the electric field created by this guy and this guy. And if this, the sum of these two effects is equivalent to this, then I just need to add these two electric fields. I can get this electric field, okay? So this needs some thinking, okay? Okay, this doesn't need some thinking. So, and then now we don't need to worry about this guy. All I need to do is just work with these two guys and find these two electric fields and add them together. Now let's take a look, but remember the electric field is a vector, so you should be careful. You don't just add these two numbers literally, right? You're going to find out the direction, and then you're going to figure out how you add these two vectors. Now let's take a look at part E. We want to find the magnitude of the electric field at the right edge of the hole. The right edge of the hole, where is that? It's here, right? And then the problem also gives us some distances, right? So this guy has a radius big R, the big sphere, and then this small sphere has a radius A, and the distance between these two centers, the problem says is going to be B. So we know these three distances. They're symbols, okay? But I'm just going to treat them as numbers. That's something I already know from the problem, okay? If I need this distance, I just use big R. If I need this distance, I use B. This distance, I use A, okay? I'm going to still have all the symbols in my final expression. I don't get a number at the end, but I'm just going to work with symbols. Now I'm going to find the point in this big sphere. So if I want to find that point on this big sphere, solid, no hole, that's just going to be this point, right? And then what is that point in this small sphere? Negative, that's going to be right edge, right? So if I can find the electric field at this point and this point, add them together as vectors, the effect is going to be the same as this guy with a hole in it, right? With the hole in it. Now, how do I find the electric field at this point and this point? First, direction. Vectors, they always have directions, and the directions is usually easier than magnitude, right? Directions, sometimes you just use the symmetry or anything, you find. You don't need to do any math. But we have already found it, right? For a solid sphere, what is the electric field created by this solid sphere? Inside or outside? Well, it's going to be outward, radiated outward. We did that in class, right? So at this point, the electric field must be in this direction. That's E1. What is the electric field at that point? Okay? This is a negative sphere. What is the direction? Totally negative, solid. What is the direction of the electric field created by this solid negative sphere? Inward. At any point, it's going to be inward. So if I want to draw the electric field at this point, I would draw it this way. Right? So how do you find these two? If you have these two numbers, what do? You're going to subtract them. You don't add them. You subtract them, right? Because they are in opposite directions. So, okay, so that's the direction. And then depending on which one is larger, I'm going to do E1 minus E2 or E2 minus E1, okay? Now these two values, okay? You do need these two values. We just figure out the direction. This value, it's going to be this expression, right? So that's when I use this conclusion, right? So use this function. And then what is the R you plug in, right? You can't just use R. You have to use one of these numbers or a combination of these numbers. So you need what is the definition of this R? The definition of this R is the distance from the sphere, the center of the sphere, to the point, right? You want to calculate. This is the point I want to calculate. Forget about that. Where's the center? The center is here. So I just need this distance. I need this distance. What is this distance? That's just B plus A. Okay? So I'm going to plug in B plus A as R. That's the E1. I will get an expression, all symbols, no numbers. Now E2. I'm going to still use the same function, right? And then use that function, rho E, it's going to have rho E and epsilon R. Now, what is this R I plug in? Well, it's at the edge, right? The right edge of the small sphere, that's going to be the radius of the small sphere. What is the radius of the small sphere? Because this is the center, right? The radius of the small sphere, A. Right? Once you have them, what do? You subtract them. You subtract them, okay? And the direction, if E1 is larger, the net electric field is going to be in that direction. If E2 is larger, the net electric field is in that direction, okay? So that's how you find the electric field created by this guy with the hole. So the left edge, where is the left edge? So it's this point. So again, you're going to do the same thing. It's going to be the electric field created by this guy at the left edge, which is here, and the electric field created by this guy at the left edge. So you're going to draw these two electric fields, the direction, right, of each electric field. Then you're going to figure out, are you going to add them or subtract them? Okay? We just figure out for the right edge, you need to subtract them because they are in other directions. For the left edge, do I still subtract them? I'm not sure. Okay? Don't use any shortcut. Okay? You just draw them out. You're going to figure out if you're going to add them or subtract them. Just take a look at these two directions. Okay? So don't remember these shortcuts. Okay? There's no use doing that. Okay? There's no point doing that. Because I pick a different point, everything is going to be changed. If everything has changed, then you can't just use the shortcut at a different point. Right? So this point, you're going to repeat the same process, right? Draw these two vectors, and again, it's going to be either you add or subtract them, because these two electric fields, they're going to still be on the same axis, right? These two electric fields are going to be on the x-axis. So you're going to plug different values here. You're going to plug different values, because the distance here is different than the distance here, right? So I'm going to leave that part for you to finish, because the left edge and the right edge, they're very similar. Now let's take a look at the part I, the top of the hole. The top of the hole, so it's different from the left and right, because now you're not going to just add or subtract them. Why? First of all, I don't know, right? I just need to draw them out. Let's draw them out. This is the top edge. I don't know how to find the electric field with this guy. Okay? Let's find the electric field at this point. And the electric field at this point, right? They're the same point. Find these two electric fields, add these two guys as vectors. Now, what is the direction of the electric field at this point? Positive solid sphere, always outward. So you're going to draw a vector outward. So this is the center. This is the center of the sphere, right? This is not. This is the center. So you're going to draw a vector outward. Okay, so you see that this E1 is not up, down, or left or right. It's in that direction. What is E2 at this point produced by this negative solid sphere? Inward. So, okay, so this E2 is still down in the y-axis. Now you have two vectors, E1 and E2. How do you add these two guys? Can you add or subtract these two vectors, these two numbers directly? You cannot, because they are not in the same direction. They're not along the same line. You can't add or subtract them. Then how do I add these two vectors together? Components, right? You're going to break this E1 into x and y. And E2, you don't need to break it, right? It's already in y direction. So actually, you're going to subtract these two guys, right? E1y and E2, they're in opposite direction. You're going to combine these two y components as a new y component, which is going to be E net y. And then you're going to get E net x. E net x is actually easy because you only have an x component, E1x here. Okay? So this is going to be E1y minus E2. If E1y is still larger than E2, right? Okay, so E2, you can still use this expression, right? Because the same expression. What is the R you should plug in for E2 at the top? Well, that's still going to be A, right? Because that's still the radius, so I'm going to still use this, okay? Because the distance is the same. What about the expression for E1? What is the R you should plug in for E1? R has a definition. You don't need to figure out R using your own theory. R is always defined. That's the distance. We call it R, but that's the distance from the center of the sphere to the point. Okay? The center is here. The point is here. Draw a line connecting them. Doesn't matter if this line already exists in this problem. You just draw a line connecting them. That's the R you need. Okay, this R is not given in this problem, right? But you can use a right triangle to help you find this line, because if I draw a vertical line here, that's the center. That's the center of the small sphere, right? Because that's the top of the small sphere. You already know this side is A. You already know this side. This side is B. You have a right triangle. You know these two sides. How do you find hypotenuse? So you see that you can find the R and plug it in. Okay, so in this case, you don't use B plus A. You're going to use this R. And you can calculate that R, okay, using this right triangle. So that's how you find the magnitude of E1. But you're not done yet. You still need to find the components of E1x and E1y. How do you find these two components? Well, then you need an angle, right? Because I need an angle so I can do sine or cosine. I know there's a right triangle here. So I just found E1 using this R. So say if I want this angle theta, how do I find this theta angle, right? The problem doesn't give me this theta angle. Again, this theta angle is this theta angle, right? Because the E1 is in that direction. If you want this angle between E1 and the horizontal, that's the angle. And then this theta angle, again, is in this small right triangle, A, BR. So I don't need to find theta angle, right? All I need is sine theta. What is sine theta? What is cosine theta? I'm just going to use these two expressions to find E1x and E1y, right? Because E1x is going to be E1 times sine or cosine. E1y is going to be E1 times sine or cosine. So I just need these two expressions. What is the expression for sine theta using this right triangle? What is the expression of this cosine theta using this right triangle? That's going to be the expressions you use to find E1x and E1y. And then you can do E1y minus E2, leave E1x here. So the interesting thing here is this. If you have done this algebra correctly, these two guys, E1x and E2, they're going to turn out to be the same expression. It's totally coincidence, okay, because of the math. There's no way you can explain that intuitively by looking at this guy. Okay, how come the y component of E1 and then cancel out E2? No, you don't do that intuitively. There's no way you can figure it out intuitively. You do the math correctly. At the end, you figure out these two guys actually cancel out exactly. So which makes the final answer a little bit easier because you only have an x component left. So at the end, you don't even need to combine these two components for this net electric field, okay? Because it's only going to have the E1x left in that direction, okay? E1y. You have to do the algebra yourself. You're going to find out these two guys cancel out, okay? And then the top point and the bottom point are exactly the same, right? And what is the difference between this point and this point? And then you can repeat the same process, right? Now in this case, E1 is going to be in that direction. Okay, if you draw E1 at this point, and then E2, it's going to be still inward, and you're going to do the same thing. You're going to break E1 into x and y, and then find the x and y components of E1, and then combine them with the E2. You do the bottom part. Okay, so it's going to be the same. All right. So I'm going to stop here. These are the two questions I want to discuss with you in homework 4.